A few weeks ago, Makera reached out to me about doing a review of the Carvera Air, this machine that you can see me unboxing. I said to them I don't really do reviews anymore, but I can tear it down to tiny pieces and show people what's inside, to which I expected them to say, no. But they said yes, so here we are. Today, we're doing a teardown of the Makera Carvera Air, a desktop CNC machine. As always, the full disclosure notice is in the description below. As I go through the disassembly without any instructions, I'll be trying to highlight some of the interesting design features as we go along. If you own a 3D printer, you're probably well aware how important calibration is to precise prints. That's why I created the Cauliflower and Cali Lantern, of which I just released the very latest design, Cali Lantern Mark II. It's a step-by-step calibration process that gives you an STL to print, measure, view the results and score, and guides you through all the corrections needed to improve your prints. You can check it out via the link in the description below. Before I started the teardown, I did use the machine just to make sure it works and to manufacture a little PCB. We start by doing a bit of engraving and then wiping on this UV curable resin, cure it under a UV lamp for about 15 to 20 minutes, drill a few holes where we put our components in, do a little bit more cutting to remove the PCB from the rest of the material, and before you know it, there's a PCB. I also cut a small part in aluminium, as that's the other material that I plan to use this machine for. As with many other disassemblies, the first place to start is removing the enclosure so we can get to the finer stuff on the inside. Unfortunately, these side panels has this kind of sticky metallic tape stuff on, and in the process of pulling it off, it kind of bends into a permanent, not flat shape, so I'm not sure those will ever go back on again, unfortunately. Certainly not as good looking as they were when they were delivered. Removing these two plastic pieces, we're able to flex the cover slightly and take it off. The hinge and sliding mechanism for the enclosure is facilitated by these nice little CNC parts, which I'm quite glad they didn't finish further because they look quite nice as they are. The sliding portion of the hinge is actually a laser cut metal piece that's part of the injection mold, which is quite cool because it requires you to put the plate into the mold before injecting the plastic around it. It means you get a permanent bond between the two without any play or wiggle. From this side, you can also see the heatset inserts, which are used to secure the grey piece to the clear cover. However, I chose not to remove them because this fluffy tape was never going to go back on once I've removed it. You can also find some magnets in this outer cover. There's these large ones with the foam surrounding it, and I believe these are there in order to basically make the cover snug the metal casing, with these foam pads then providing some grip and damping to basically reduce noise and vibration of the cover when the machine is in operation. There's also this very tiny one by the slide, and this operates a Hall effect sensor so the machine knows when the door is closed. Large square panels with lots of screws in them often hide secrets underneath. This upper panel hides access to the drag chain or the rear of the printer, as well as the main electronics enclosure in this midpoint, where I also noticed some cables going down into the base, which we'll take a look at in a second. The overall layout here seems pretty logical. As you can see, the fan intake on the right, the managed cables to allow for airflow, and then a clear output on the far left-hand side. The main control board sits at the back of the enclosure, with all these wires connecting to it, and a smaller PCB at the front is the electronic speed controller for the spindle. We'll take a look at these a little bit later on. This bottom panel doesn't have anything behind it because that's the space where the bed goes, but it does help with access. Flipping the printer over, we can see the huge die-cast frame which makes up the lower portion of the printer, as well as some massive rods, large bearings, stepper motor, ball screw, and the wires which come down for the stepper motor end stop and, annoyingly, the bed. These plastic P-clips are a great way to manage cables because they're totally reusable and they secure the cables very well. So getting out two of them was easy, but this last one was not so easy. I couldn't work out quite how it was attached. It sort of went behind the bearings and up behind the bed. So now it's time to remove the bed. The corner anchor is used to help position parts, and then you have a 2mm MDF waste board, a 15mm board for screws, which help for mounting of the parts, and then the bed plate itself is 8mm of aluminium. And then here we find the cable, the dreaded cable which I couldn't get access to, and still, even after removing all this, can't find a way to get it out. So, time to remove more things to try and find how this cable is attached. This steel plate is a protective piece to stop the chips getting into the bearings, which are obviously placed below the bed. These are just laser cut pieces of thin stainless steel. With those few screws removed, we can wiggle it out to get a bit more access. Alas, not enough access, so now it's time to remove the bed. All the screws for the bed, as well as many others in the machine, had some sort of Loctite material on it, a sort of thread-locking plastic that holds the screw in under lots of vibration, which of course you do have a lot of in a CNC machine. Happily, with the bed removed, we can finally see a hidden zip tie with no other way to access other than by removing the bed. Not perfect, but at least it was secure. With the cables clear of the machine, I can now start to remove this top part of the enclosure. This enclosure body is a folded and welded sheet metal fabrication. Of course, its main job is covering and protecting a number of parts of the machine, as well as providing a high-quality external finish. But despite my best efforts, there was always one more screw to remove. At this point, I thought the fan was the only thing still holding it in, so I removed the screws for the fan, and yeah, it still didn't come off. The breakout board behind this clear cover had some wires which were connecting into the main control board, which needed to be detached in order to remove the cover. But once that was done, the whole thing did just slide off. Pretty easily, kind of mostly. You pretty much get in there, and then it came off. One weird part of the enclosure was these washers stuck over the holes that seemed to be helping the enclosure fit the part beneath it, as acting as little spacers to prevent any rattling. Not a beautiful solution, but it does seem to work. On the inside of this enclosure, we can see this breakout PCB, which connects things like the LED, front button, and Hall effect sensor for the door, which you can see right here. And there was also this extra cable, which you can see here, which was labeled CAM. So maybe you can also add a USB camera to this device? I don't know. For now, let's take a look at all the electronics and wiring, starting at the tool head. There's a number of screws around here to take off little panels and covers and things, which is a great idea, as you don't want metal chips getting onto your end stops or connectors, etc. Wiring is quite often one of those things that's left as a bit of an afterthought and ends up a little bit slapdash and not very well done. In this case, I think it has been well planned in. There's definitely routing paths and things planned for all the wires. I would say that the cable chains in general are a little bit overstuffed because you need quite a bit of space in those for the cables to move. Pretty much all of the wires in this machine are covered in this thick plastic sleeving, which would help quite a lot if it's rubbing up against plastic. But if you accidentally get chips in your cable chains and those metal chips start rubbing against the cables, it's going to get through. I think it's almost certainly better to have this protection rather than not, but it won't protect from the overstuffing of the drag chains. Taking a break from the tool head area, I head round the back to some of the mains power delivery section and the speed controller. In a CNC machine like this one, a speed controller is really essential, as you need an accurate and consistent speed of that spindle in order to get the right feeds and speeds for cutting the material accurately and consistently without damaging either the part or the tool. To distribute some of the heat generated by the speed controller, there's a large heatsink on the back, and of course there's airflow through this part of the enclosure via the fan which we mentioned earlier. One of the details that you might easily overlook, but I really liked in this electronics enclosure, is the connectors. That might sound pretty sad, but it's quite interesting because they've noticed that it's very easy to plug things in the wrong place and therefore potentially cause damage or incorrect operation. So every connector here is either a different size or a different color, and that way everything will pretty much only go in one place, making it very easy to connect things up to exactly where they're supposed to go without making any mistakes. It sounds like an obvious thing to do, but many don't, because there are huge cost savings to having all the connectors exactly the same. Then you only need to source one type of connector, one type of terminal, and it makes manufacture a lot quicker. But ultimately, it's the user side, which is more important here. As you can see, there are quite a lot of wires in this machine, and plugging them back in the right place is going to be easy because they're all labeled and color-coded exactly. With all the wires out the way, now we can take a closer look at the control board, of course, once it's removed. The first weird thing is that the SD card sticks out this daughter board that's sort of soldered in the middle of the PCB. My initial reaction was definitely one of confusion, but then I realized from the external panel, this is going to be much easier to access than one on the side of the board. The other weird thing is there's a stepper driver here. Just the one, but there's sockets for 3. I presume this is for the 4th axis, which gives you another rotary axis with which to machine, so you don't have to rotate the part around. This is particularly useful for maybe cylindrical type objects. Despite the rest of the machine also using stepper motors, we'll see why there's not stepper drivers in a moment. From this perspective, you can also see quite how many different connectors and sizes there are on this board. As I mentioned, it doesn't seem like any of them are used twice, all unique by either size or color, so nothing connects in the wrong place. Heading back to the wiring, this is the drag chain, which is, I think, particularly overfilled. It is really stuffed full of cables, and that's not quite the right way to use a drag chain like this. That being said, relative to a 3D printer, the amount of motion and relative speed of that is definitely reduced, so the requirements would be a little bit less. Perhaps one of the most disappointing oversights of this machine is the power supply. Although it may seem minor thing to many, this LRS 450 watt unit doesn't meet the harmonic current requirements for use in the European Union. As with many other parts of the build, the electronics enclosure is a welded sheet metal fabrication, and these two more pieces around the front which cover the ball screw. These are stainless steel, which should look pretty good, but they have this little black line around the edge, which I'm guessing is from the adhesive and the laser cutting, where it's just sort of melted on and they've not cleaned it off fully. It doesn't affect the functionality, but the aesthetics definitely take a hit. I really liked at this point how you could see all the main functions of the printer, so I thought I'd give you a little spin around so you can have a look for yourself. So moving on to the main tool head disassembly now. As you can see, there's this big sheet metal part where the fan is attached and there's going to be the motor on the inside. But in order to remove the handle, you have to remove this kind of first part of the handle in order to get to the screw, which is then on the inside of the handle bit. For a moment, I suspected the one on the opposite side that I'm doing now would go all the way through and both parts would come out together. As you can see, that was not the case, and I eventually found the screw on the inside and managed to remove it. I probably wouldn't have done it this way if I'd have known, but this is all without instructions, as always, so I have to just make a guess as I go. But as you can see, I eventually got it all off, and then this whole sheet metal housing comes off too, and you can see the motor and spindle kind of stuff below. As we move through disassembling more of the tool head, you'll start to see that it's basically kind of adapter plates upon adapter plates to adapt one thing to another thing to then another thing as well. Oh, and by the way, if you're wondering why there's these pen marks across lots of the screws, it's typically done as a way to identify if screws have come loose. Now we have the spindle removed, we can try and take a look inside, although we'll have to do it just with pictures because the video that I took seems to be lost or corrupted somewhere. We start with this adapter plate, which has, as you can see, some pins, and that allows the whole assembly to locate properly onto the panel behind it, as well as a keyway in order to mount the motor correctly to the plate. Of course, this spindle is absolutely essential that it's perfectly vertical, or at least as close as possible, in order for the cutting to be also vertical. In case you weren't sure what bit does what, the bottom part, which is the black and dark grey, is the motor, and the boxy bit at the top, which looks kind of like a gearbox, is the part that allows the tool to be changed without any additional tools. From here, you can see the coupling within the gearbox, and there's a small rubber piece that goes in the joint between them to take up any slack in the positioning of those two pieces, as well as potentially impacting the torque response. There's also this plate on the back, which I thought might cover some part of the motor interior, but it's just a cosmetic cover. Unfortunately, despite my best efforts to remove every single possible screw, I couldn't get any further into this assembly to see how the mechanism worked. This was the part that arguably I was actually kind of most interested in, but I think you need some kind of special tooling or something to remove parts of this, because from here I just had no way of removing anything else. Everything was just kind of spinning on the spot and rotating. I tried pulling and pushing and everything. I just couldn't get any part of this to move any further than it already is. So that's it, I'm afraid. That's as far as that bit goes. Next up on the tool head, we have another huge adapter plate. This joins the 4 linear carriages together, as well as the arm which does the vertical motion, and translates that into an adapter plate for the spindle to mount onto. This thin sheet metal part in the middle is a cover for the Z ball screw, which does obviously the Z axis motion. It was a little bit of a weird one to disassemble because it has a strange order of operations. The cover itself doesn't come off on its own. You have to remove the top and bottom of the ball screw assembly in order to get the whole thing off together. Taking a closer look at the Z-axis assembly, we can see the pillow blocks at each end, as well as the ball screw in the middle and the actual carriage sitting on the ball screw, with the arm which attached to the adapter plate, which then attaches to more adapter plate and the spindle, etc. The design of the block on the left-hand side means that it takes all of the axial forces from the rod. The bearings are clamped both sides of the block, meaning that that block will take any load which is applied lengthways across the ball screw. The other end just has a single bearing and then the pulley to receive the belt from the stepper motor. Around the back now, I'm removing the Z stepper motor, which attaches to the ball screw via a 6mm belt, which I have to be honest is thinner than I was expecting. Taking a look at the stepper motor, 3D printer users might be familiar with this as a NEMA 17, except there's something a little bit different, which is this adapter on the bottom. It seems to be a servo adapter by MKS. The main difference here between a stepper motor and a servo is that a servo has a closed feedback loop, meaning it has a way of sensing what the position of the motor is and then feeding that back into the input to adjust for any inaccuracies in the current position. On AliExpress, I found pretty much the exact thing that Makera are using in the Carvera Air, although it does have some slight adaptations for their specific implementation. By finding this, we now obviously also learn that communication from the control board to these adapters is done via CAN, and then the stepper driver is actually integrated into this adapter, which then drives the stepper motor. Next, we move on to disassembly of the X-axis motion components, and firstly detach the ball nut from the cast carriage. This releases the ball screw from the carriage, and then we should be able to release the whole thing by then removing the stepper motor, and of course the pillow block on the other end, which is holding the whole lot together. On the far left-hand side, you can see the pillar block with the two flange bearings and the nut which then basically clamps the ball screw all together, and that piece takes all the axial load on the ball screw. On the far right-hand side, we of course have the servo-adapted NEMA 17 stepper motor and a coupler between the stepper motor and the lead screw. At first, I thought this type of coupler would be problematic because it can stretch in the axial direction because it's basically like a spring. However, because the ball screw and stepper motor are both hard mounted at two ends, there's actually no opportunity for any load to pass through the coupler. It was at this point that I noticed this large metallic sticker on the back and wondered what on earth it was there for. Was it hiding something? But of course, it was just covering the holes where the rods slide in. But now you can see why it was there, and the adhesive is actually really easily removed as well. So if you need access, that is how you can do it. You can see here that I'm trying to remove some of the grub screws and screws that attach like the whole frame together because I wanted to remove the carriage and all this kind of stuff. However, they seem to all be attached with red Loctite or something similar, as there's no amount of force that I could apply that would turn these screws at all. Red Loctite is basically permanent, but you can release it with some application of heat. However, the very large aluminium frame with lots of surface area would have easily sunk away more heat than I can actually apply, so I'm not sure there's really anything I could have done to release it. Also, some of the screw heads are basically completely inaccessible, so I've literally no idea how they got these screws in the first place, but there's no way that I'm getting them out. Much like the X and Z directions, the Y-axis motion system also uses a similar stepper motor, ball screw, pillow block, and ball nut assembly, with an addition of a drag chain and a wider mounting plate for the two bearing components on either side. There's not too much to see here that's very different to the other axes. Same stepper motor, same end stop switches, ball screw, pillow block, drag chain, and a thick folded piece of steel to attach to the bearing carriage. And of course the NEMA stepper motor also has the same servo converter thing on the back. One interesting part about this assembly is the sheet metal bracket, which holds the ball nut to the bearing blocks. Because of the way it's designed, unless it's manufactured absolutely perfectly, it will either push the blocks outwards or pull the blocks inwards, just because the mating faces oppose each other. As a result, you have a bearing misalignment, which causes a lot of friction and potentially jams your motion system. They've tried to overcome this by undersizing the bracket very slightly and then shimming it to the correct size. It seems like a weird way to do it, as you're still limited by the manufacturing precision of the shim, which, again, is unlikely to ever be absolutely perfect. To me, it seems like a better way to do this would be to use mating faces which are coplanar, so you can just have a flat piece of sheet metal with some small slots to allow some wiggle room, and then when you clamp down your fasteners, you align it perfectly every single time. Since I'm unable to take this frame apart any further, we'll take a look at it like this. The frame itself is made of three large die-cast aluminium pieces. There's the base, which is a large ring, and then the two vertical struts on either side, which hold the X-axis gantry. The round hardened steel linear rods used for the X and Y axis are a 20mm diameter and a 12mm ID giving a 4mm wall thickness. The linear rails for the Z-axis are 15mm wide, and all three axes are driven by 12mm ball screws. A number of areas have been masked or machined in order to improve tolerance in areas where it's specifically needed, or to assemble or add screws and things like that. Let's cover some of the summary points about this machine. Overall, I think the design of this machine is really quite good. It's clearly been well thought out and planned. As with every design, there are little places where things are not quite perfect, but I think they've handled these reasonably well, and overall doesn't really affect the overall performance of the machine significantly. The core motion system is well designed, although potentially more torque from the motors may be a limiting factor as you really push the limits of this machine. When it comes to maintenance and repairability, overall, you can dismantle most of this machine. There are limitations when it comes to red lock type things, which you just can't undo, but by and large, there's a lot of the smaller parts which can be fairly easily replaced or repaired. However, access to these parts is limited. Their spares catalogue online doesn't seem to really list much of the parts that are available, although this may be different if you contact their support directly with a specific issue. However, their biggest limitation here is the repair and maintenance guides online, for which there's basically not much as far as I can see. The wiki seems to be mostly empty and quite sparse, although the bigger brother, the Carvera main machine, does seem to have a few more details, so maybe they'll get to it, just it's not there yet. If you enjoyed this teardown of the Makera Carvera Air, don't forget to like and subscribe to Vector 3D. While you're down there, leave me a comment telling me which machine you want me to tear down next. Also, remember to check out our calibration tools at vector3d.shop. Thanks very much for watching, and I'll see you in the next one where we try not to destroy more things.